Okay, so I'm recording this, please, and I start to put the Bekenstein bound for a black hole. S is defined. The maximum amount of information that a system can hold is this, right? A is the area. S is the maximum amount of entropy of a system. So maybe I just speak here. System A of area A can hold, right? And basically this is it happens can hold. Right. So basically, it's related to for the black hole. So there's the extreme situation of a system, right? So where I repeat again, A is the area of this is the black hole. So I'm going to say that A is the area of my system, in that extreme condition. L sub P is the Planck length, right? The Planck length, as I mentioned, is defined. If you go below the Planck length, there is no physical meaning, right? So basically, how I can compute, for instance, the amount of information is that you basically compute that area, right, in units of Planck length surfaces, and that's the result it will later will appear the fourth, because we need only the surface of that. Okay, the surface of the system. That's the reason why it appeared there. For this is, if you read the paper on Lloyd, you will find why they came this, right? Okay, and K sub B is the Boltzmann constant. So LP is LP, just for your information. LP is the Planck length, that is the Planck length, that is 1.61 626 times 10 to the minus 34 or 35 minus 35 meters, right? So it means that if we go belong to shorter to that length, there is no physical meaning, right? It loses any kind of physical meaning. And K sub B is the Boltzmann constant. Now we have to remember also to take into account the associated Shannon entropy. That is very interesting. Okay. In bytes, in bits, right? H is this. So there is a relationship between the entropy and the information, right? So it says that S is equal to H multiplied by the natural logarithm of 2 times K sub B. Okay. Okay. So we have this. Right, so I'm going to make this. I'm going to put this in the center. So, mm, and I'm going to put this cell convert to traditional form. Okay, so I repeat again, there is a relationship between the Shannon entropy in bits H and the entropy, right? There is this very famous formula, right? Then what we have, then we have that H. So if you combine these two equations, we have that H has to be less or equal than this, right? A divided by 4 times log of, remember this log is natural logarithm, L sub P square. That's it. There it is. So we have now a relationship in between the actual information in bits and the area of my device. There it is. Format. I'm going to put in the center, and after I'm going to put this cell convert to threshold to give it like this. Okay. So there it is. I have this, right? So that was important to remember this. This was expressed, by the way, in the document where we were talking about the Shannon entropy in bits. So the little relation, as you can see, you can express the entropy and the memory bits with these relations. Very nice. Okay. Okay, so now it's time. Now we have all the elements that so we can apply for the cell button. So then for the cell avatar, so we are going to apply for our case. For the cell avatar, right? For the cell avatar, then the maximum, the maximum information that can be stored in, remember the device of the cell avatar is this one. I'm going to copy anyways this. I can paste it here. No, let's copy like this. Let's copy this here. So I'm going to copy this. Put this there. So you see the element is 100 millimeters square. So for the cell avatar, then store in what is this? In 100 millimeters square, right? 100 millimeters square. Right? So phase in bits is this, right? So I'm going to put the maximum will be equal to this. Will be equal to this. A over this. Let me see. A over this, you see? And now, please, this is, I'm recording. In Mathematica, you can do this. So instead to assign values directly, I can say this is A, is this value, right? What is the area? The area is 100 millimeters. So I have to transform these millimeters to, I have to transform these millimeters to meters squared. 100 divided by 1,000, right? 10 to the 3, right? Square. Sorry. This square. Right? So I transform these 100 millimeters to meters. So 100 millimeters, 1 millimeter, there is, 1,000 millimeter, and one meter, there is 1,000 millimeters. This square will be meters squares. Okay, so the area I have a meters squares. So because if I transform it in international units, I will get the value in bits that I am interested in, right? Is the Planck length is this value, right? Is this value? Is this? What is this? It's 1.662 and to the minus 35, right? 35. What else? And that's it. The rest is this. This is a log. Sorry, this is have to correct this. This is log of this. Okay, so we have this. I have everything here. So the maximum memory bits is this. Remember what is the maximum? What is the maximum memory of the universe in bits? Then today. You see, we're safe. It means that it makes sense. The solution makes sense, of course, because small devices. But it is in bits. Now let's make sense of this amount of this. Any question to here, please? Somebody. Questions to people. Juan, do you have any question? Brit, any question? Tony? Edward, do you have any question? Then. Huh? Okay. So that is it. So that is, remember, that this will be in bits. Right. So let me check this and to make sense, in petabytes, right? So let me check this. In petabytes, bytes. Remember, this is bits. Bytes is it has to be with 8 times, right? So you have to divide it by 8. Just in case, 8 bits is equal to 1 byte. That is in your computer you have bytes, the unit of bytes, right? So let's check this because you have eso was you were okay. Remember this, just 8 bits is 1 byte. In your computer, we have the memory. We use the units of bytes. That's the reason why we have to do this proper transformation. Okay, so the maximum will be in petabytes will be I'm going to put like this in PB. That is petabytes. This is the acronym of petabytes will be maximum, right? The maximum we compute multiply by we have to divide by 8. So we have in right now we have in bytes. And how much is 1 petabyte, please? 1 peta. How much is one? Peta? And to the bytes. Remember, that is the unit we have, right? So we have this, so 1 petabyte to the 15. So we are going to have how much information this is in petabytes. Still, it's a big number, right? In terabytes, let me check in terabytes. Terabytes. TV. It's will be the same, right? But now divided by how much? Terabytes. Now you can ask, right? Terabyte. You have driver. What is the size of your hard driver, Tom? Around 1 tera, right? Probably it's 1 tera. You see, this device has 52. 10 to the 52 of the same. Easy. You cannot even imagine this amount, right? And this is small device. So, anyways, so just to compare to make sense this number, okay? I'm going to put just for your curiosity as a reference is estimated, right? Just is estimated. The maximum amount of information that our brain, can hold. That is based on some stats is around 2.6 times 10 to the 40, 10 to the 42. You see, this is bits. Or in more familiar, 3.25 times 10 to the terabytes. Now you see. So it's approximated that the brain can hold this amount of memory. The question is, what is that memory? Remember, memory is everything we know plus memories of smells, memories. We can go, with sounds and everything, right? So it's like huge. So it makes sense. So the brain has 10 to the 29 terabytes. So the 20 to the 29, let's say if you want to compare, if my computer this computer has 1 terabyte of the hard drive, so I have to use 10 to the 29 terabytes to compare with the memory of okay, just in case. Okay, so just to give you some comparison to StepMixer. Now let's go. Now let's check the computer power. According to Leo, to lot. This paper, Lloyd's paper, right? You remember this Margus? We called it the Margolus Ledkin. Theorem states that the maximum, the other one, that was the computation, the maximum logical operations per second depend on the energy of the system. And this, I'm going to put this floating point operation second max, like this, max. It is less or equal to the energy of the system, right? Divided by this. What is the maximum? Pi times h bar. This is that is the maximum logical operations, floating point operations, right? So this take it into the center, and this I'm going to put this to traditional. See, this is according to this Margolus-Lepkin theorem. This says that you have the energy of my system. That system, the maximum computation, the operations that can make it depends on this. Okay, so that's it. So then for our Salvatore, we have what we have for the Salvatore. We have this float. I'm going to put like this flops max is equal to 2 times. Sorry, here is 2. So here is 2 times is the total 2 times the energy. So times this energy divided by this. But now we have the h bar. Okay, so we have this. Now, since remember this is the floating points, Now the flops max per second will be if we divide this E by T, we are going to have the power. So just we have so instead I'm going to put the power. So the power is how much? Is 20 watts. Why 20 watts? Or 20 joules in 1 second. So this is the power. Why we use 20? Because this is the power that the brain uses to operate. So that's the reason why it's a nice measurement. And what is H bar is 6.626. 626 times 10 to the minus 34 joules divided by 2 pi. See? Like this. So this will be the total computer power that we can have the system, right? In the system. In petaflops, will be this loss of mass multiplied by 1 divided by 10 to the 15. You see, why in petaflops I like to use? Because remember, 1 petaflop is the order of magnitude of the computer power of our brain. So it means that this Salvatore has the power of 10 to the 20 human brains. It's just, we cannot imagine this, right? So this is the, I think that this is enough for this, okay. If we want to let's put in exaflops to compare with the computing facilities we have here. In exaflops, Oops. We are going to do this, right? Divided by 10 to the 18. See? To 7. Remember, in the world, we have around not even 100 exaflops in the whole capacity of the right now. Current capacity of the world is 10 to the 2. Less than 10 to the 2. See? Yes, 10 to the 2. So you see, now you can imagine how much computational power you're going to have in the future. What are you going to do? Somebody he say, I don't want this. I will think. Okay. Please, this is only for you guys. I'm not going to rate this to you guys. And I'm going to compare your notebook. So now you can compare what you need to the students who try to challenge yourselves. What we have. Okay. Questions here? Any questions? You need some coffee, maybe. Okay, guys. We'll stop here 5 minutes. We continue lecture in 5 minutes, please. If you have any question, please let me know. This is remember, this is only for your reference. I'm not going to grade this only for you guys. Okay, I'm going to pause this. I'm going to